Hello everyone, myself Santanu Samai. I pursued my BSc from Midnapur College Autonomous and currently I am going to join IISc Bangalore for integrated PhD program. My first interview was at IMSc Chennai and I am going to discuss my interview experience. And there were 4 professors. Then first professor asked me to introduce myself. Initially they asked me some questions on quantum mechanics and they asked me the first question: draw the simple harmonic oscillator wave functions. And we know that simple harmonic oscillator potential. We know that simple harmonic oscillator potential is half m omega square and x square, where omega is the angular frequency of the simple harmonic oscillator. And then they asked me to draw the ground state to the fourth excited state wave function. We know that the ground state wave functions is a Gaussian type wave functions and it looks like this is the fast excited state wave function. And we know that the total number of nodes in the wave function should be 1 for the simple harmonic oscillator. And we clearly see that here only 1 node is present. And similarly, the second excited state wave function is this is the second excited state wave function. And this is the third excited state wave function. This is the fourth excited state wave function. And then next they asked me for which state delta x and delta px will be the minimum. We know that for simple harmonic oscillator, delta px and delta x have the form n plus half h cut, where h cut is the reduced Planck constant greater than equals to, and we clearly saw that for n equals to 0, delta px and delta x has minimum value. So delta px and delta x have minimum value for ground state, means n equals to 0 state. Then they asked me to find out the value of delta x and delta px for simple harmonic oscillator. And we know that delta x and delta px greater than equals to commutation of x comma px and expectation value of it and its modulus by 2. And we know that commutation of x comma px should be I cut, and if we take its modulus, then I vanishes and only h cut remains, so it should be h cut by 2. And then they asked me to prove delta x and delta px for ground state wave functions from the basic level. And now I am going to derive these expressions. And we know that for ground state, if we represent the ground state k of 0, and we know that delta x should be, means delta x means deviations in positions, and it should be equals to root over of expectation value of x square minus expectation value of x square. And we know that for simple harmonic oscillator, expectation value of x always 0, because if we look at the wave functions of the simple harmonic oscillator, then the wave function should be even, should be symmetric or asymmetric about the origin, means x equals to 0 wave function. So so expectation value of x would be 0 for simple harmonic oscillator. And we know that x square expectation value should be for ground state and we can write x square in operator form like that. We know that x can be written in the operator form root over of h cut by 2m omega into a cap dragger plus a cap, where a cap dragger is the rising operator and a cap is the lowering operator. And if we write these expressions here, and it will be h cut by 2m omega into a cap dragger plus a cap and a cap dragger plus a cap into bra of 0. H cut by 2m omega comes out from these expressions, and now it will be and we know that if we operate this rising operator with any state n, then it gives root over of n plus 1 and k of n plus 1. And when lowering operator operate nth state, then it gives root over of n and n minus 1. So here n should be 0, and if we put n equals to 0 here, then the expression should be root over of 1 means once and only 1, and here we put n equals to 0, then this expression should be 0, so it basically 0. Now we operate this operator with fast excited state, then it will give put n equals to 1, then we it will give root 2 into k of 2, plus if we operate this lowering operator with the fast excited state, means if we put n equals to 1 here, then it will give 0. Here if we put 1, then it will give root over of 1 into 0, k of 0. So it is basically h cut by 2m omega of into 1, because we know that k of bracket notation of 0 and 2 should be 0, because they are different state, means they are orthonormal each other, and we know that for same state it should be 1. And we know that delta x square expectation value of delta x square have the value h cut by 2m omega. Now I have to find out the delta of px. We know that delta of px is the deviations in momentum of the particle should be equals to root over of expectation value of px square minus expectation value of px the whole square. And we know that as we look into the wave function of the simple harmonic oscillator, the wave functions always real, and we know that for real wave function expectation value of momentum should be 0 when for real wave function, and we have to calculate expectation value of px square. Now we know that expectation value of px square should for the ground state and if we takes these constants from these bracket notations, then we get m omega h cut by 2 minus of m omega h cut by 2, because here the iota is present. So if we take the iota square, then a minus sign arises. So it is basically a cap dragger minus a cap into a cap dragger minus a cap of 0. And if it operates with the ground state, then it will give 1, and if this lowering operator operates with the ground state, then it will give the 0 result. And if it again operates with this fast excited state, then it will give root over of 2 into ket notation of 2 minus 0, ket notation of 0. And if this bra operates with these brackets functions, then it will give only minus 1, because we know that bracket notation of 0 2 is 0 and bracket notation of 0 and 0 should be 1. So finally we get m omega h cut by 2. So we can now calculate delta px equals to root over of m omega h cut by 2, and delta of x will be root over of h cut by 2 m omega. So if we multiply these deviations, delta x into delta px, and it should be h cut by 2 m omega into root over of m omega h cut by 2. M omega cancel out, and finally we get h cut by 2. Then they asked me the next questions: what is the minimum time required to go from ground state to the excited state using unitary operator? We know that the expressions of the unitary operator is e to the power minus of I e t by h cut, and we have to excite the ground state. We have to excite the particle from the ground state to the excited state, and let's say ground state is psi naught, and we have to excite it to the fast excited state psi 1. Now if we apply multiply this unitary operator with this ground state, then we get the wave function psi naught into e to the power minus of I E naught T by h card, where E naught is the ground state energy of the wave function. Means at that moment I don't give the proper answer of these questions, but I told them that as the x functional dependency of psi naught and psi 1 is different, and unitary operator have only the function of t, then if we multiply the ground state wave functions with this unitary operator, then its time dependency changes, but its x dependency does not changes. So I think we don't get excited state from the ground state using the unitary operator. Then professor did not make any remark on this answer, and they then asked some questions on electrodynamics. Basically, the second professor asked me some questions on electrodynamics. Then they share me a screen, and the problem was like that. And then they asked me, draw the field lines if this substance is a conductor. Now I am going to draw the field lines. And we know that the field lines enter into the conductor makes to 90-degree angle with the surface of the conductor. So field line started from the positive and it goes to the negative like that. But when it starts from here and it ends with the conductor surface perpendicularly, and similarly it creates from the other surface perpendicularly and ends with the negative surface of the conductor, and it also creates from here and also it ends with the surface of the conductor perpendicularly, and it will be like that, and for here it will be like that, and it will be like that, and it will be like that. Here we see that the field lines does not exist inside the conductor, because we know that the electric field lines does not exist in conductor. And then the professor asked me, why you draw the field lines such that, means field lines makes 90-degree with the surface of the conductor, and I given derivations of that. We know that the conductor is an equipotential surface, means if we take a surface of the conductor, suppose S, and take 2 points A and B, and let's say suppose here the electric field is E, at the point is E, and it makes an angle theta with the surface. Now if I am going to move a charge, Q charge, from A to B point, then the work done by the worker against the field should be curve integral of a to b e dot dl. Here dl is the length between a to b, means dl equivalent to ab. Again we know that the surface is the equipotential, conductor surface is equipotential. So if we move a charge from one point to the another point, we don't have to work any, we don't have to, we know that if we, for a conductor as basically the conductor is an equipotential surface, so we don't need any work to move this charge from a point to b point. So integration of a to b q into e dot dl means basically the work done should be 0, and we know that, and here we know that here q is not 0 and also dl is not 0. So basically E perpendicular to dl. So E must be perpendicular to the dl. So the field line should be perpendicular to the surface of the conductor. And then they asked me why the electric field line does not exist inside the conductor, and I give some logic in favor of my statement. We know that for a conductor there have large amount of free electron inside the conductor. So when we apply the electric field, then these free electrons moves against the directions of the electric field. Means we know that electrons is basically negatively charged, so it moves from the opposite to the directions of the electric field, and after some times the electrons moves to these sides of the conductor, and these sides of the conductor should be positively charged, and at a certain time the intrinsic electric field, we know that here created some electric field because here the positive charge and here the negative charge. So here created some intrinsic electric field, and its direction should be opposite to the external electric field, and for a particular time these two electric field, means internal electric field and external electric field, should be equal and opposite, and so the net electric field inside the conductor should be 0. Then they asked me some questions. Then the third professor asked me some questions on classical mechanics. And he asked me what happens when we make a tunnel inside the earth and put a particle in the tunnel with velocity 0. Let's say this is an earth and this is a tunnel, and this is the center of the earth O, and the radius of the earth is R, capital R, and let's say the particle at a instant of time t, the particle is here at the point t, and the distance of this particle from the center of the earth is x, and if we apply the Newton's second law, means F equals to ma, then we get that the force experienced by the particle should be minus of, because the force is minus signs arise because the force It's directed toward the center of the particle, center of the earth. So it should be m, mass of the particle, and g, where g means the gravitational accelerations at the point t, should be equals to m into d2x by dt2, and it will be d2x by dt2 will be minus of g. And if we calculate g from the Gauss law, we know that closed surface integral of g dot ds, here the gravitational accelerations is g dot ds should be equals to the minus of 4 pi g into mass enclosed within this Gaussian surface S, and it should be equals to the 4 by 3 pi x cube into rho. Rho is the density of the earth, and if we solve it, then we get closed surface integral of g into ds. Here g dot ds should be g into ds because g and ds should be in the same directions. So g dot ds should be equals to minus of 16 pi square g by 3 rho x cube, and it should be g into 4 pi x square equals to minus of 16 pi square g rho by 3 into x cube. This x square and 3 cancel out, pi cancel out, 4, and we get the expressions of g minus of 4 pi g rho by 3 x, and if we put this g value here, then we get basically here g and ds should be in the opposite directions, because we know that gravitational force is always attractive, means it's directed from toward the center. So here and ds, we know that the elementary surface always outward from the surface. So here g dot ds have some negative sign, so here arise some negative signs, and this negative sign cancel out, and it becomes positive signs. And if we put this g expressions here, so we get minus of 4 pi g rho by 3 into x. Basically it is the expressions of simple harmonic motion expressions. So the particle oscillates inside the tunnel, and then they asked me what is the velocity of the particle at the other surface, at that point here, and we told them that basically we know that gravitational force is conservative in nature, so the energy will be conserved at every point inside the tunnel. And if we look at that point here, the particle velocity, initially the particle velocity is 0, so its kinetic energy T should be 0, so and its potential energy V should be minus of g m. M is the total mass of the earth into small m, mass of the particle, and r is the radius of the earth. And here also V should be same, and so as energy will be conserved, energy will be same here and here, so T will be basically 0 here. So T will be 0 means V should be 0 here, means the particle's velocity should be 0 here. And then the next professor asked me some questions on the thermodynamics. Then they asked me what happens when an astronaut opens the cap of a bottle on the surface of the moon. we know the Clausius. To solve this problem, we have to know about the Clausius-Clapeyron's equations. We know that the Clausius-Clapeyron's equations dP by dt equals to L latent heat by T into V2 minus V1. This V2 and V1 is the specific heat of the final state, and V1 is the specific heat of the initial state of the substance. And we know that at the moon the dP should be negative because the pressure on the surface of the moon should be lower than the pressure on the earth. So dP should be means final pressure minus initial pressure should be negative. So as for the vaporizations, L is positive and T always positive, and for the vaporizations the final state is the gaseous states and the initial state is the liquid state. So always V2 minus V1 should be positive. So make this expression positive, we have to put dt should be dt equals to positive. Dt should be negative because dP is negative, so dt should be negative. So the boiling temperature of the water reduces, and we told them, and I told them that the water becomes vaporized. Then they asked me, what about the latent heat? Basically they asked me what is the source of the latent heat, for which the water that comes into the vaporization state. Initially I don't say the proper explanations, but then they gave me some hints, and then finally I told them that some amount of water transform into the vapor state to take the latent heat from the rest of the water. Means if some water gets vaporized and some rest of the water becomes cooled down, means its temperature decreases, and after some step some of the water becomes in the solid, means ice form. Then they say yes, it is right. And this is my last questions of my interview, and fortunately I got selected at IMSc Chennai.